Hello and welcome to this session on information retrieval. So this is the big picture of what we are discussing, and today we'll continue our discussion on relevance and ranking. Just to give you a recap, we can model sentences as vectors. We start by defining the dimensions of our vector space, and then we place our vectors. We have worked out this example in our earlier lecture. If you have not seen this, I urge you to go back and see the previous lectures. So we simply place the dimensions, and then each of these numbers give the term frequency of each term. Let's say bits appears once in the query. So that's how we form this term document incidence matrix. And then we have the vectors. For instance, q is 1 1 0 0 0 0. And once we have the vectors, we could use cosine similarity measure to compute the similarity between query and the documents. One factor to note here is that every time when we compute similarity, we don't want to compute the magnitude of the vector. So we could always pre-compute it at indexing time, and we could store the document vectors as unit vectors. Uh, so D2 over the L2 norm of D2 would be a unit vector of D2 and so on. So whenever a query arrives, we compute the query vector, and then we find the similarity. So the picture looks something like this, and the similarity would simply be a dot product. All right, so here is a vector for you. Can you length normalize this vector and arrive at a unit vector for the same? Take a minute, pause the video and work it out. If you got this answer, kudos. So all we have done is find the magnitude and divide each element by the magnitude. So we got the unit vector 1 over root 6, 0, 1 over root 6, and 2 over root 6. So if we have a vector of this kind, how do we find the cosine similarity? So here I give you two unit vectors. Can you find the cosine similarity between them? Again, pause the video, please work it out. The answer must be close to 1. All we have to do is take the dot product between these two vectors. Since these are already unit vectors, we don't have to, we can just ignore the magnitude. We discussed term weighting, where I told you that not all terms have the equal weight, and some of the terms might be good enough to be ignored, in which case we would like to assign a weight of 0 as shown in this example. And we also discussed that inverse document frequency, IDF, could be a good candidate for a term weight. And we also discussed the need for length normalization. So I had said that it's easy to misdirect a search engine towards a document which repeatedly uses a query word um, just to take all the queries to that fake website. Now we don't like this, and we want to avoid this. We want to length normalize the documents usually, and here is one formulation which allows us to length normalize the documents. Let's call this TFL or TF sub L. Just like length of the document matters to us, also the distinct number of occurrences also matters to us. Here is one example. Let there be two documents of equal length, let's say 20 terms, and but however, let's say they differ in the number of distinct terms in each of them. So let's say distinct terms in D1 is 5, and distinct terms in D2 is 15. And let's assume the term frequency of IIITD in D1 is 4, and term frequency of IIITD in D2 is also 4. So in this case, you see that document length is the same, which is 20, and we also see the term frequency as the same, which is 4 for the query term. So why should the distinct terms of D1 and D2 actually matter? Why would you prefer one document over the other? This is also a good moment to pause the video and think. Well, this is what is going on here. So let's consider D1, D2 to be these documents, right? So D2 is the real document, let's say the official page of IIITD, and it has a sentence which goes as welcome to the official page of IIITD. And let's assume it also has a few more sentences. IIITD has 4 departments. IIITD has research focus. Come to IIITD, schedule visit. So this seems to be like a genuine document. Now let's see a D1, a fake version of D2, which I created. And let's say I want the search engines to visit my page and not go to D2 whenever a query IIITD comes. This can happen if both D1 and D2 have either the same score, or D1 is better than D2. So how can I do this? So simply I could say IIITD works in IR, Venkatesh works in IIITD, in IIITD, Venkatesh works in IR, Venkatesh works, IR works, IIITD works. Some junk content going on over here, doesn't matter. But if you see, both of them have the same length 20, and both of them have IIITD appearing 4 times. But we want to prefer D2 over D1, and one way to catch these kind of fake websites is by counting the number of distinct terms of D1 and D2. Quite clearly, D1 could be of topic IIITD, Venkatesh, or IR, because we see these 3 terms repeating very often. But in the case of D2, it's only IIITD that repeats, and the rest of the terms are kind of distinct. So D2 has more number of distinct terms than D1. Now this can be a useful clue when it comes to ranking documents. But how do we use this idea in our scoring function? So here is version TF sub R. There it is, TF sub R of IIITD over D1, which simply does TF over the average TF of the documents in our corpus. Um, so here is an example. In D1, we have 20 over 4, that's 5, and 20 over 1.3 would give me 15.4 in the case of D2. I'm sorry, this is the average TF of the particular document DJ. So, here we see that D1 clearly um, uh, gets a lesser weight, lesser TF value, whereas D2 gets a higher TF value for IIITD, because IIITD is the most repeating term in that document. So we have seen 2 versions of computing term frequency, the TF sub L and TF sub R. So I call this the length regulated TF, or LRTF, and we usually call this the relative intra-term TF, or the RITF. So when do we use these documents, and how do we decide which one to use? So here is a case where RITF fails. Let's assume D1 has 20 terms and D2 has 200 terms, and the distinct terms in D1 are 15, distinct terms in D2 are 150. And we have the same term frequency of IIITD in both. Now, which document would you prefer? Well, if we try to work this out, we see that in the case of RITF, which is simply TF of the term triple ITD over the document over the average term frequency, we see that TFR of triple ITD in both document 1 and document 2 are the same. So when we have a proportional increase like this, TF R is not really useful, and in these cases we prefer TFL instead. Okay, there's another ranking function which is quite popular called the Okapi ranking function. This was first implemented in the Okapi information retrieval system at the London City University, and ever since we have had many variants of this. These ranking functions are called best match or BM followed by some version. So BM11, BM15, BM25, BM25F, and so on. So let's take a look at one of these, which is the most popular one called the BM25 ranking function. So the idea is still the same. The score is computed as a sum of TF-IDFs, and we stick to the usual formulation of IDF, which we have discussed before. The thing that differs here is the term frequency calculation. So let's assume f of q comma d gives me the frequency of the query term qi in the document d. If that is the case, so instead of just using frequency, I use this kind of a formulation where k1 and b are free variables. So empirically, we have found that k1 in the range of 1.2 to 2.0 is quite good, and b at 0.75 gives best results. But this is largely corpus dependent. Let's try to understand this function a little bit. You must be already familiar with the length normalization that's happening over here. So what's interesting is the way K1 and B are used. Um, to start with, let's assume K1 is 0. Then what happens? Please pause the video here and try to understand what happens when K1 is 0. If k1 is 0, we see that this second part, second term in the denominator disappears, and the numerator simply becomes a frequency, right? So if the numerator is frequency and the denominator is also frequency and there's no second part of the denominator, then both of them cancel out, and all we are doing is using the IDF alone. So we totally ignore the frequency information. So that's what happens when K1 is 0. What happens when B is 0? You must have noticed already that when B is 0, this whole factor becomes 1. So we simply add K1 to the frequency in the denominator. And what's happening in the numerator is simply k1 times the frequency. So if you look at it, this is simply a function of frequency and nothing else. So the ranking is not affected at all when compared to using simply a frequency information, right? So this is equivalent to just using TF IDF here without any kind of length normalization. So K1 and B play such interesting roles in this formulation, and by adjusting K1 and B, we can tune to the length or to the extent to which we want to apply length normalization in this case, and that's the beauty of this formulation. So this formulation has been quite popular across the information retrieval system, and we stick to this in many or several information retrieval systems. All right, let's move on to another interesting idea, which is if we are only interested in top K documents, usually that is the case. So when you have millions and millions of matching documents, it's humanly impossible to go and look at all the documents. So usually we are interested only in the top, let's say 100 or 1000 documents. So if it is given that we are only interested in top k documents, how can we improve our matching algorithm? Note that applying VSM or cosine similarity on every document against the query is quite expensive, and we would like to reduce the candidate set of documents on which we want to apply VSM. How can we do that? The idea is to guess the candidate set, which is much smaller than the entire corpus. We call this the inexact top k retrieval. There are many ideas to do inexact top k retrieval. Here are a couple of examples. The first one is called index elimination, where we consider only those documents that have an IDF which is greater than some threshold. And this usually works like a charm, because if the inverse document frequency is greater, that means the documents that are in our candidate list are shorter, and thereby we save a lot of computation. Or we could also consider only those documents that have several query terms in them. Right, so the one which has the most number of query terms is likely to give a higher score, and hence this heuristic also works. A caveat here is that these are only heuristics, and they don't guarantee that the top scoring document will always be in your candidate set. We don't have such guarantees, but the documents that we return could still be good enough uh, for good precision and recall. We could also use a champions list. A champions list is a pre-computed set of top docs for certain query terms. The intuition here is that we already know certain query terms as popular query terms, or terms that we appear more often from the users. So we assume we know our users here. So if that is the case, I could always pre-compute and keep a set of documents and just return them. We call this as the champions list. Um, we could also do another smart thing while we are constructing our index, as we have shown here. So let's say each document has some popularity score, which is given by a function g of d. Then I can add popularity to my cosine similarity measure and have a net score of query to document as g of d plus the cosine similarity score. If this is the case, then a simple trick of just ordering the document IDs in my postings list by the function g of d or by popularity, that's the trick, because I don't have to go beyond a point to retrieve, because we are only interested in top k documents. Another similar idea which is useful is called cluster pruning. In cluster pruning, what we do is at query time, we consider only a small number of clusters for matching the queries. So assume you have a large vector space and you have lots of documents all across your vector space, and assume that these documents form some kind of clusters. So we know that our query term is, let's say, topical in kind. So let's say it's a healthcare query, sports query, or something like that, and assume certain kind of topics lead to certain kind of clusters of documents which contain similar terms. In which case, I don't have to look at the entire vector space. I can only look at some parts of the cluster. Usually we start with, so let's assume we have n documents in our corpus. We usually start with root n documents by random, and then call them as leaders, and then take all the related documents which are near to those leaders and form clusters, and from there we decide which cluster my query matches, and then explore that cluster in more detail when I compute my vector space, when I compute my scores, cosine similarity scores. Another idea here is to use tiered indexes. The idea of tiered indexes is to have multiple indexes, multiple versions of indexes. So we have the dictionary. For the same dictionary, we split our postings list in such a way that tier 1 index contains only those document IDs which have term frequency above some threshold for a specific term. So as is evident from here, this is done in cases where we already know that these are popular terms that would appear in a query, and it's worth creating an index for that. So this extends the idea of champions list that way, and we can come up with multiple tiers, and we start matching from the topmost tier and then keep going till our k value is met for top k retrieval. And there is also this idea of proximity weighting. Ideally, query terms should occur closer to each other in the document. So let's say I have a document such as CMI is located in Siriseri, and let's assume the query is CMI Siriseri. So the intuition here is that the documents which have CMI and Siriseri as close as possible should be a better match than the other cases. If that is the intuition, then the score or the value, let's say we define a proximity score W, which gives us the smallest window containing these query terms. So in this case, if I have to match this document D, then W should be at least 5. So we have 1, 2, 3, 4, 5 terms in this window, and unless if the window size is less than 5, I might miss one of the query terms CMI and Siriseri. So I need to have it at 5 to match this document. So now that we have this kind of a measure W, the question is, can we somehow incorporate this into a scoring function and use it to prune the results? So this is another idea that we use while scoring. Of course, there are many ways to design a scoring function using W. So we stop here in this lecture with the idea and not get into the formulations of the scoring functions. So if putting everything together, the complete search system looks something like this. We start with documents, we parse them. So there is a document processing pipeline, and there is also a query processing pipeline. On the document processing pipeline, we have the indexers, the crawlers and the indexers who are interested in creating different kinds of indexes that we have seen so far. So this also includes zonal indexes, top K retrieval related algorithms, tiered indexes, K-gram index, and so on. On the other hand, we also have a query processing pipeline where we do things like spell correction and so on. Of course, spell correction also happens on the document. Actually, I should correct myself. We don't need to do spell correction on both ends. As long as we do spell correction on the query processing end, we are good enough, because now we could do the matching directly with the document. But then you could ask, what happens when the documents have spelling errors? Um, the assumption here is that the likelihood of documents having spelling errors is far lesser than query having spelling errors. So that's why we don't do it on either side. Depending on the kind of search system you use, if you are in a domain where the documents can have too many spelling errors, then you might like to put the spelling corrector on the document processing pipeline as well. Okay, once we have these, we are interested in matching, and the scoring and ranking algorithms play a big part over here. So this is where the BM25s and the other scoring functions like cosine similarity come into picture. Sometimes we might also use learning techniques to find, let's say, the term weights. And if we have to do that, we of course need to know the relevance training sets, some human provided relevance data, or we assume that the clicks are a good proxy for training sets, and we sometimes use click data instead of the training set. And finally, we are ready with the results, and we produce them through a results page. So this is a very crude high-level overview of how a complete search system looks like. Here are a couple of good readings if you are interested in knowing more about TF-IDFs, LRTF and RITF, for instance, Giaul-Pike's Sigaya 2013 paper on TF-IDF weighting schemes is a good read from that perspective. And there is this seminal work on probabilistic relevance framework, which talks about BM25 and beyond, from Stephen Robertson and Hugo Zaragoza. With that, then, look forward to meet you again for another session on information retrieval. Thank you.